When you ask an AI to generate an image, it doesn't sketch outlines or mix colors. Instead, it starts with an absolute blizzard of pure, chaotic static, and gradually sculpts that noise into a stunning masterpiece. This is the magic of diffusion models. The core idea is brilliant but counterintuitive. To teach an AI how to create, we first teach it how to destroy. We take a perfect image and slowly corrupt it with static until nothing is left. The AI learns to reverse this destruction. In the forward process, we mathematically inject noise into the image. Think of the image as a vector of pixel values. At each time step, we scale down the original vector slightly and add a small vector of noise. This destruction forms a Markov chain. That means each corrupted state depends only on the immediate previous state. We shift the mean towards zero and increase the variance until the image is indistinguishable from random static. The noise we add isn't just any static. It follows a Gaussian distribution. This means the pixel values cluster around zero. Because Gaussian noise is well understood, it gives us strict mathematical guarantees. Applying noise step by step is slow. Thanks to the reparameterization trick, we can combine all those tiny noise additions into one formula. This allows us to fast forward time and jump instantly to any noisy state. Now comes the hard part, the reverse process. If we could calculate the probability of the previous slightly cleaner image given the current noisy one, we could walk backward. But that requires knowing the distribution of all possible images. Since we cannot compute the true reverse probability, we use a deep neural network to approximate it. The AI acts as a proxy, looking at the noisy image and trying to predict exactly what noise was added. Another way to view this is through the score function. The score is the gradient of the log probability of the data. Essentially, it computes a tangent line that points uphill toward more realistic images out of the noise. The engine driving this prediction is usually a U-net. It uses two-dimensional convolutions to compress the image down into a tight bottleneck of high-level features, and then expands it back out to the original size. These convolutions act like a sliding window systematically moving across the image. As the window scans over the pixels, it detects local patterns like edges and textures, building an understanding of the visual geometry hidden beneath the noise. But convolutions only see small local areas. To ensure a dog has exactly 4 legs, the network uses self-attention in its deepest layers. This allows pixels on the left side to communicate directly with pixels on the right. To decide which parts of the image to focus on, the attention scores must be normalized. We use the softmax function to exponentiate the raw scores and turn them into a tight probability distribution, highlighting what matters most. How does the AI know to draw what you typed? This is text conditioning via cross-attention. The model computes the dot product between the image features and your text prompts embeddings, physically steering the denoising process. Training the model is remarkably simple. We calculate the mean squared error between the actual noise we added and the noise the network predicted. Then we use gradient descent to walk down the loss surface. Once trained, we can generate art. We sample a grid of pure Gaussian noise, set our timer to step 1000, predict the noise, subtract a small fraction, and repeat. Step by step, the image emerges. To make the image align strictly with your prompt, we use classifier-free guidance. By applying vector addition, we extrapolate the difference between conditioned and unconditioned predictions, pushing the final prediction further in the prompt's direction. Doing all this math on high-resolution pixel grids is incredibly slow. Models like Stable Diffusion use latent diffusion. They compress the image into a smaller mathematical space, making generation lightning fast, without losing quality. Advanced models treat this not as discrete steps, but as a continuous flow through time using stochastic differential equations. By solving these equations and integrating over time, we can generate higher quality images in fewer steps. Diffusion models have revolutionized artificial intelligence. By borrowing principles from thermodynamics and combining them with deep neural networks, we've taught machines how to sculpt order out of pure mathematical chaos, turning noise into breathtaking reality.